Now let's see the topic of the session, equations reducible to quadratic form. Sometimes there are some equations which are not directly in the quadratic form, but we need to do some substitutions to then reduce to the quadratic form and then factorize. So let's see some of the example problems which demand for reducing to the quadratic form. To start with an example problem, say I wanted to factorize 7 power 1 plus x plus 7 power 1 minus x is equal to 50. Then I want to factorize this or solve is the question. Then I clearly see that this is not in factorized in the quadratic form, and therefore factorizing this would not be an easy task. So let's attempt to see if I can reduce the given equation into the quadratic form. So for example, 7 power 1 plus x, I split using the law of index. A power m plus n is a power m times a power n, and this can be written as 7 power 1 by 7 power x, because a power m minus n is a power m by a power n, the law of index, which is equal to 50. Now proceeding similarly, I get this to be, taking LCM or multiplying throughout with 7 power x, I get this to be 7 power 2x plus 7 equals 50 times 7 power x. So I have multiplied the whole of the equation with 7 power x in this form. So multiplying with 7 power x, I get this to be this 7 power x into 7 power x is 7 power 2x using the law of index, and then this reduces to 7 and this, because this gets cancelled, and then 50 times of 7 power x. Now from here, let's rearrange 7 times 7 power 2x and minus 50 times 7 power x plus 7 equals 0. So I bring all terms to the left. Now with this, let's see how I can convert the obtained equation into the quadratic form. So for this, what I do is let 7 power x equal to some t, because this gives me an understanding that when 7 power x is t, then my 7 power 2x is 7 power x times of 2, which is t square. Therefore, I can write 7 power 2x as 7 power x whole 2 using the law of index. A power m is a power m whole times of n is a power mn, and therefore I get this to be this, but this is nothing but t, which is substituted in place of inside the bracket, so that t square. So I have 7 power x is t and 7 power 2x is t square, which I am going to substitute in this quadratic equation, in this obtained equation. So let's see what I get. In the first case, this is 7 times t square minus 50t plus 7 equals 0 is what I get when I substitute these two in the above equation. Now this clearly is a quadratic equation which is obtained to be reducible to quadratic form. Therefore, this equation is substituted with 7 power x equal to 2 after further simplification, and then that gives me a quadratic equation in t. Now it is not a tough task for finding the factors for this quadratic equation, and the factors of this quadratic equation indirectly give me the factors of this given equation. Thus solving the given equation is the intention behind equations reducible to quadratic form. So therefore here, let's factorize the 7t square minus 49t minus t plus 7 equals 0. So I get two values, 7 and 1 over 7, through which I'm going to simplify. So there are two values I got. T is 7 and t is 1 by 7. Now when t is 7, my t is nothing but 7 power x, which I'm going to substitute here because I have this equals this. And in this case, 7 power x is 1 by 7, which is 7 inverse, which I can write for this. Now, when the bases are equal, the powers are equal. Therefore, this gives me x equal to 1. And when the bases are equal, the powers are equal. Therefore, this gives me x equals minus 1. Therefore, the solution of this given equations are x equal to 1 and minus 1 is how we understand the equation which is not in quadratic form reduced to the quadratic form by substitution of this in the quadratic integral, and then that gives me the values of x indirectly. This is how we understand equations reducible to quadratic form. Now let's see a theorem through which we understand the common root concept connected with a property. So the theorem says here that the necessary and sufficient condition for the quadratic equations a1x squared plus b1x plus c1 equal to 0 and a2x squared plus b2x plus c2 equal to 0 are the two quadratic equations which I considered, and the theorem states that the necessary and sufficient condition for the quadratic equations this to have a common root is that I have c1a2 minus c2a1 whole square equals a1b2 minus a2b1 times b1c2 minus b2c1 is the condition which I need to prove both as a necessary and a sufficient condition. So let's see how we can derive the proof of the given theorem. Now, as we read the statement, we clearly understand that there are two quadratic equations which are given with the condition to have a common root. So because we don't know what a common root is, let's take the common root of these two quadratic equations as some alpha and then proceed with the proof to finally get this equal to this. Now coming to the proof, let alpha be the common root of the quadratic equations a1x squared plus b1x plus c1 equal to 0, a2x squared plus b2x plus c2 equal to 0, which I take as equation 1 and equation 2. Now because alpha is the common root of this equation 1 and equation 2, that means alpha is the root of 1 and 2 independently. That is, when we say that alpha is the root, it must satisfy the given quadratic equation because it's simply the root or the solution of the given quadratic equations. That implies I get a1 alpha squared plus b1 alpha plus c1 equal to 0 and a2 alpha squared plus b2 alpha plus c2 equal to 0, which I take as 3 and 4. And this is because since alpha is the root of equation 1 and 2, this is because alpha is the root of both equations 1 and 2, giving me this and this. Then what I do is consider b1 times of equation 3, a2 times of equation 3 minus a1 times of equation 4. So here finally what I'm doing is I multiply the whole of equation 3 with a2 and multiply the whole of equation 4 with a1 and then subtract. So let's see what we usually get. So when I multiply equation 3 with a2, I get this to be a1 a2 alpha squared plus a2 b1 alpha plus a2 c1 equal to 0 is what I get when multiply equation 3 with a2. Similarly, I multiply equation 4 with a1, I get a1 a2 alpha squared plus a1 b2 alpha plus a1 c2 equal to 0. And then I subtract these two equations. So on subtraction, I get this cancelled because these two are the same terms under subtraction. So finally, I take alpha common and I get a1 a2 b1 minus a1 b2 plus a2 c1 minus a1 c2 equals 0. So therefore, if I continue from there, I get this to be minus alpha times of a1 b2 minus a2 b1 equals a1 c2 minus a2 c1, because when I bring here it comes as minus, which can be adjusted for these two terms interchanging. Therefore, when I bring this out here, I get alpha times of a1 b2 minus a2 b1 equals c1 a2 minus c2 a1 is what I get for the given expression. So I take this as equation 5, and then let's see how we can take the other set of simplifying the equation 3 and equation 4. Now similarly, let's see if what happens when I multiply equation 3 with b2 and equation 4 with b1. That is, I consider in my next case b2 times of equation 3 minus b1 times of equation 4, and then see what exactly the subtraction leads to. So when I multiply equation 3 with b2, I get this as a1 b2 alpha squared plus b1 b2 alpha plus c1 b2 equals 0, and then from equation 4 multiplied with b1, I get a2 b1 alpha squared plus b1 b2 alpha plus c2 b1 equals 0, and then I subtract so that this time this is the common term which gets cancelled. So proceeding as in the previous case, I take this common and I get a1 b2 minus a2 b1 times of alpha squared equals plus c1 b2 minus c2 b1 of this equals 0 is what I get when I simplify using the subtraction process. Now taking this into consideration, I get this to be further simplified as a1 b2 minus a2 b1 of alpha squared equals, I bring this to the right, which comes as b1 c2 minus b2 c1, which I take as equation 6. So I got totally two equations, equation 5 and 6, which I'm going to consider to get this condition. So let's see how we can obtain the condition using this in consideration. Now these are the two equations which have obtained from multiplying the equations 3 and 4 respectively and then subtracting. So with these two equations, what I do, I just take equation 5 and squaring on both sides of equation 5, I obtain on the left hand side alpha squared of a1 b2 minus a2 b1 whole square equals c1 a2 minus C2A1 whole square. This is clearly when I square on both sides of equation 5. Now I try to use equation 6 in this, is the intention behind. So in this case I can split this as alpha square times A1B2 minus A2B1 times A1B2 minus A2B1, because this is square which can be split in two different terms. That is equal to C1A2 minus C2A1 whole square. The reason behind splitting the two terms of the square is that from equation 6 I have directly alpha square of this as B1C2 minus B2C1. So this can be substituted for this. Whole square is what I get when I substitute this here. So rearranging, I get this to be the left hand side of this term is C1A2 minus C2A1 whole square is A1B2 minus A2B1 into is what we get as the necessary condition. Now, assuming that alpha is the common root, I proved that this equal to this is called necessary condition. Now, assuming that this is equal to this, I prove that alpha is the common root will be the sufficient condition, the reverse process of the necessary condition and its proof. Is how we understand the necessary condition through the proof. Now let's see the sufficient condition of the theorem. Now let's take the sufficient condition, that is assuming that for the given two quadratic equations which are given by equation 1 and 2 in the previous case, we have the condition which states C1A2 minus C2A1 whole square is equal to A1B2 minus A2B1 times B1C2 minus B2C1 is what is the necessary, the sufficient condition out here. Now with this, I prove that there is a common root between two quadratic equations. So to start with the proof, I take two cases where in case 1, I assume with two cases. So let's take the case of, there are two cases through which I'm going to prove the sufficient condition. So in the initial case, I assume that A1B2 minus A2B1 is equal to 0. So using this equal to 0, I prove for the common root, that is the sufficient condition. So because A1B2 minus A2B1 is 0 on the case 1, that implies substitution in this equation gives me C1A2 minus C2A1 is also 0, since we have this condition which we have taken in the sufficient condition. Now with these two conditions, let's see what exactly I get. From the previous assumption of case 1, I get this as A1B2 equals A2B1, and from this I get C1A2 is equal to C2A1. Now proceeding similarly further, I get this to be A1 by B1 equals A2 by B2 is what I rearrange these terms. Now from this, I arrange this in the form C1 by A1 equals C2 by A2. So I have got totally two cases of A1 by B1 is A2 by B2 and C1 by A1 is C2 by A2. Now if I assume the given quadratic equation A1x squared plus B1x plus C1 as say A1, B1, C1. To avoid the lengthy simplification of this, I assume this quadratic equation in this form, and then I assume the other quadratic equation A2x squared plus B2x plus C2 as A2, B2 and C2 is what we get. Now, if I assume for these two quadratic equations in the triad forms, then therefore from this I get this by taking common of A1, I get this as 1 B1 by A1 C1 by A1. By taking A1 out, each of this gets reduced as 1 by A1 and 1 by A1 of this. So indirectly we assume the quadratic equation in the form with A1 times of 1x squared plus B1 by A1 of x plus C1 by A1. This is written in triad form. Now here, I get this B1 by A1, which we have as B2 by A2, if I interchange, can be written as B2 by A2, because A1 by B1 is A2 by B2. Therefore B2 by A2 is B1 by A1, substituted for this using this condition. Similarly, my C1 by A1 is C2 by A2, which comes out in this form out here. So therefore, when I multiply A2 inside, then I get A2 comes out, and this reduces to A2, B2 and C2, because each of this is multiplied with A2, where A2 gets cancelled here, and this 1 times of A2 comes in this way. Again, bring back A2 inside, I get 1 B2 by A2 and C2 by A2, that is taking A2 outside the bracket. Now as I see this, I see that this is A1 by A2 of A2 B2 C2 is A2 x squared plus B2 x plus C2. Therefore, I have the first quadratic equation which can be expressed as a multiple of the second quadratic equation. This making us understand that therefore A1 x squared plus B1x plus C1 equal to 0. Therefore, by taking this quadratic in this form, I have an A1x squared plus B1x plus C1 equal to 0. Then indirectly this A1 by A2 times of A2 x squared plus B2x plus C2 will be equal to 0, where this brought to the right gives me, if and only if, A2 x squared plus B2x plus C2 equal to 0, assuming that A1 by A2 is not equal to 0. Therefore, this makes me understand that when this is 0 implies the two given quadratic equations 1 and 2 have same root, is how I understand the case 1 of the sufficient condition. But it's very important to identify here that I can take A1 common with A1 coming in the denominator, because A1 is not equal to 0. When I have A1 equal to 0, the whole of the quadratic equation reduces to linear form. Therefore, in this case, A1 is not equal to 0, and in this case, A2 is not equal to 0. So each of A1, A2 is not equal to 0. Similarly, we have the case 2 through which we can prove the given sufficient condition of the theorem.